Let us continue our Module 1 discussion. In this video lecture, we will be focusing on propositional logic. So how do we transform a proposition into its equivalent mathematical equation? We use small letters to represent one proposition. For example, P, Q, R, and S are used to express a proposition. Each variable can be true or false. We have sentences that are composed of more than one proposition. And this sentence, we call it compound proposition. To connect the different propositions in a sentence, we use logical connective or functions like negation, conjunction, disjunction, implication, and biconditional. So let us discuss first negation or not function. A not operation switches the actual value of the proposition. Suppose the original proposition is true, then if we negate it, the statement will be false, and vice versa. The symbol for not are these two symbols, and it should be written before the variables. So let's have an example. Let P, today is Sunday. So when we negate P, we negate the predicate or the fact about the subject. So the result will be today is not Sunday. If we want to determine the possible result when we evaluate a statement, we may use a truth table. The truth table shows all possible states or values of the proposition and its corresponding status when we evaluate the whole statement. Like in this truth table, the first column shows all possible values of P, and in the second column shows the corresponding result when we negate is implemented, when negation is implemented. So when P is true, when we negate it, it becomes false. When the original statement is false, when we negate it, the statement will be true. So that's how negation works. So now let's move on with the next operator or operation. It is conjunction or and. A conjunction is a compound statement formed by combining two statements using the word and. In symbolic logic, this is the symbol to be used. Okay, so in symbolic logic, the conjunction of P and Q is written as this: P and Q. Okay, so let's have this example. P, today is Sunday. Q, it is sunny. So if we have P and Q, so the equivalent in English, today is Sunday and it is sunny. Okay, and this is the truth table for and. Again, a conjunction is true only if both the statement in it are true. Otherwise, the statement is false. Okay, so now let's move on with the third operator, which is disjunction. A disjunction is a compound statement formed by combining two statements using the word or. This is the symbol for or. Okay, so let's have this example. So this is how we write or function. So P or Q. Let P, today is Sunday. Q, it is sunny. So when we read this in this mathematical equation in English, it is equivalent as today is Sunday or it is sunny. Okay, and this is the truth table for OR. As you can see on the truth table, as long as there is a true proposition, the statement will be true. Okay, the statement will be false if all proposition in the statement is false. Okay, so that's disjunction. So by the way, we have two types of disjunction or operation. Okay, so we have inclusive OR and exclusive OR. The previous slide discusses the inclusive OR, wherein the statement is true if at least one of the proposition in the statement is true. So for example, I will eat chicken or pork this lunch. So I'm going to eat chicken or pork or both. Will make this statement true. Okay, so while the second type of OR is exclusive OR, SOR or XOR. In XOR, the statement will be true if and only if one of the proposition is true, but not both. Okay? So for example, soup or salad comes with the meal. So we can get a soup, either soup or salad, but not both. Okay? If we're going to get both, we're going to have an additional charge for it. But in case we want to retain the charge or the cost, we're just going to choose one of it. So that's an example of exclusive OR. Okay, so the symbol for exclusive OR is plus inside the circle. This is the truth table for XOR. So one proposition should be true, but not both, to make the statement true under exclusive OR or SOR. Okay, so now let's move on with the fourth function or operator, which is implication. An implication, also known as conditional statement, if statement, is a type of compound statement that is formed by joining two simple statements with a logical implication connective or operator. The symbol that is used to represent the logical implication operator is an arrow pointing to the right, thus a rightward arrow. So it is denoted that if P implies Q, P arrow Q, which is read as P implies Q, so today is Sunday implies it is sunny, or if today is Sunday, then it is sunny. So that's the meaning of P arrow Q. Okay, and also, by the way, in P implies Q, P is the hypothesis, antecedent, or premise. Okay, while Q is the conclusion, consequence, or the result of the if statement. So implication come in many ways. So aside from if then statement, if proposition comma proposition, we have these alternative ways in writing or reading implication. So we have if B then Q, P implies Q, if P comma Q, P only if Q, Q unless not P, Q when P, Q if P, Q when P, Q whenever P, P is sufficient for Q, Q follows from P, Q is necessary for P, a necessary condition for P is Q, and a sufficient condition for Q is P. And by the way, as you can see, in the different form, conclusion can be written first before the consequence, like here, Q when P. So kindly memorize these different forms of implication so that you will correctly identify which is the conclusion and the premise of the statement. Okay. So how do we determine will be the statement true or false in an implication operation, under implication operation? So based on this truth table, as long as the premise and consequence have the same value, the statement will be true. True, true, therefore the statement is true. False, false, the statement is true. But if not, we need to check the value of consequence, just the consequence. Okay, so if the consequence is true, like on the fourth row, false true, so consequence is true, so the statement will be true. Otherwise, like on the third column, the statement is false. Okay, so again, if we have different values for the premise and consequence, always check the value of the consequence. The consequence value will determine if the statement is true. Okay, if premise and consequence have different values, the consequence value will determine if the statement is true or false. Okay, again, true false is false, false true is true. Okay, so let's have this example. If you get 100% on the final, then you will get a grade of 1. So let P, you get 100% on the final. Let Q, you will get a grade of 1. Okay, so if P is true, you get 100, but Q is false. Your instructor didn't give you a 1. Okay, so what does it mean? The result was not achieved. Did it happen? Therefore, the statement is false. So regardless if the premise was achieved, but the result was not achieved, therefore the whole statement is false. And the statement of that instructor is actually a lie. Okay, so therefore, that statement is false. While if P is false, Q is true, the statement is true because the result happened, even though the student did not meet the requirement. Even the student didn't get 100%, the professor gave him a grade of 1. So it happened. The statement happened. The consequence happened. Therefore, the statement is true. So that's the logic behind implication. So therefore, as long as the conclusion is met, the statement is true even if the premise is not achieved. For the values for the premise, for having a different value for the premise and the consequence. Okay. Now, in case we are changing the premise or the consequence of the statement or introducing negation to our statement, the meaning of the statement may change or it could be altered. The change could be converse, contrapositive, or inverse. So if you say converse, the original statement, okay? So in the original statement, the original premise, which is P, will become the new consequence, while the original consequence will become the new premise. So P implies Q, it will be written as Q implies P in converse. While in contrapositive, we're going to introduce negation on both premise and consequence of converse. So we have not Q implies not P. That's contrapositive. While inverse, we introduce negation on both premise and consequence of the original statement. So we have not P implies not Q. So by changing the premise and consequence by introducing negation, what will happen to our original statement? Will the converse will be the negation of the original statement, or will the meaning of the statement will be the same? So let's check using a truth table. So based on this truth table, when we change the order or when we change the premise and the consequence, okay? So from P implies Q to Q implies P, they are not equal, okay? It doesn't mean that P implies Q and you change the order, they will be the same. They will have the same meaning. It's not the same based on this truth table. So for example, if you are intelligent, then you will pass the course. We can say that if you pass this course, you are intelligent. Why? Because there are different ways in passing this course aside from being intelligent. Am I right? So that's why conditional is not equivalent to converse. Okay? So if you're using this way of thinking in doing logic or using in a critical or scrutinizing statement, it's a big wrong. It's a big X. Okay? It's incorrect. Okay, so you cannot change the order. By changing the order means changing the meaning of that statement. It's a big no-no if you are using this as your way of proving something. It's incorrect. Conditional is not equivalent to converse. Okay? Now, let's compare conditional and inverse, introducing negation on both premise and consequence. Inverse is not the negation of conditional statement, as you can see here in this table. Okay, P implies Q is not the negation of inverse. Okay, but if you can see, inverse and converse have the same result. Therefore, inverse and converse are equal based on the truth table. Okay, now let's compare conditional and contrapositive. As you can see in this column and the column of contrapositive, they have the same result, same values. Therefore, conditional is equivalent to contrapositive. P implies Q is the same as not Q implies not P. So therefore, we could write P implies Q as not Q implies not P, or vice versa. Okay, we're going to use these forms when we prove something on the next video lectures. Okay, so again, conditional, contrapositive are equivalent, inverse, converse are equivalent, but conditional is not equivalent to converse. Don't forget that. Okay, so now let's move on with the last condition, last function, last operator, logical operator, which is biconditional. The biconditional statement is P if and only if Q. Okay, this is the symbol for biconditional, double-headed arrow. So how do we determine if the statement is true in biconditional? If both P and Q have the same value. Okay, both true, both false, the statement will be true. Otherwise, the statement is false. Okay, alternative meaning of biconditional is if P, then Q, and if Q, then P. So it means that we have two implication and operation for biconditional. Okay, more discussion about this when we discuss logical equivalence about this statement. Okay, so just accept it first, accept it now that P if and only if Q is the same as P then Q and if Q then P. Okay, so now these are some of the alternative ways in writing and reading our biconditional statement. So P is necessary and sufficient for Q if P then Q, and conversely, if P if with double F, Q. That's by conditional alternative ways. Okay. So as a summary, negation from true to false, from true to false, false to true. While conjunction, okay, as long as there is a false proposition, the statement is false. While for or, as long as there is a true proposition, the statement is true. While for XOR, the statement will be true if at least one of the statement, if the one of the proposition is true, but not both. Conditional, the statement will be false if the premise is true while the conditional is false. Otherwise, it's true. While for biconditional, PQ should have the same value, otherwise it is false. Okay, so again, these are the logical operators that we are using for logical proposition. Okay, so this will be our last slide for this video lecture. Thank you for listening and see you on the next video lecture. Thank you.